Now see this question. A variable speed drive rated for 1500 rpm, 40 Newton meter is reversing under no load. So what do you mean by that? Electromagnetic torque is given 40 Newton meter. No load means TL is equal to 0. The given figure shows the reversing torque and the speed during transient. Find the moment of inertia. Therefore, what is the basic equation? J into d omega m by dt plus b into omega m. Let me write down the full equation first. TL is equal to TE, okay, where TE is the electromagnetic torque developed by the motor. Now, strictly speaking here, this is a 40 Newton meter. Now here, let us assume that as a coefficient of friction is not given, let us assume it is 0, TL anyhow it is mentioned 0. So what is the moment of inertia formula from this? J is equal to TE minus TL divided by d omega m by dt. Anyhow TL is 0. Now first let us find out what is d omega m by dt. What is d omega m by dt? Rate of change of speed. The speed changes from minus 1500 to 500. So final speed is 500 minus 1500. This is given in RPM. You have to convert into radian per second. So multiply with 2 pi by 60 divided by in a time span of 0.5. Okay. Therefore, J is equal to TE, where TE is 40, and you substitute this calculation d omega m by dt. So if you put it in this equation, you will get 0.096 units for moment of inertia kg meter square. Okay, so this is the answer. Let us take next problem. A separately excited DC motor, that means flux is constant. Let me write down here. Separately excited DC motor means flux is constant when it is fed from single phase full converter. Okay, here converter is given that single phase full converter. It is operating with a firing angle 60 degree. It is operating with a firing angle of 60 degree and runs at 1000 rpm. Speed is equal to 1000 rpm. If this motor is connected to single phase semi converter with the same firing angle, what would be the speed of the motor? So when it is connected with a single phase full converter with alpha is equal to 60 degree, so first let us try to find out what is V0. What is V0? So what is the formula for single phase full converter V0? 2 Vm by pi cos alpha, right? So as alpha is given 60 degree, 2 Vm by pi into cos 60 is 1 by 2. Therefore, it will give you Vm by pi. So, what do you mean by this one? Okay, let me move forward. Now, the converter is operating with a single phase semi-converter. Now, converter is single phase semi-converter. In this case, what could be the output voltage of the converter? If you recollect rectifies chapter, single phase full converter, average output voltage is equal to Vm by pi multiplied with 1 plus cos alpha. When alpha is equal to 60 degree, what could be this value? 1 plus 1 by 2, correct? Cos alpha or cos 60 is 1 by 2. So, this will give you 3 by 2 or 3 by 2 into Vm by pi. 3 by 2 into Vm by pi. Now, observe carefully here, no other data given in case of DC motor. So, let us assume that ideal condition. Therefore, I can say that EB is proportional to speed of the motor, correct? So, as if you consider motor is ideal motor, okay, EB is equal to Vt if Ra is neglected, armature resistance is neglected. Therefore, what could be speed of the motor? Let me take a ratio like this, N2 by N1 is equal to EB2 by EB1. So, second condition corresponds to single phase semi converter, first condition corresponds to single phase full converter. Therefore, N2 by N1 is equal to, second case the voltage is 3 by 2 into Vm by pi, first case the voltage is Vm by pi, okay. So, you can cancel this Vm by pi and Vm by pi, and then N2 is equal to 3 by 2 into N1, where N1 is the speed of the motor when it is operating with a single phase full converter, that is 1000 RPM. Therefore, it will give you 1500 RPM, okay. It will give you 1500 RPM. So, option B is the correct answer. Now, let us look into the next problem. A single phase half controlled converter, which is nothing but single phase semi converter, drives a separately excited DC motor. The motor has a back EMF constant of 0.5 volt per RPM. Armature resistance is 5 ampere without any ripple. Let us note down the data first. Back EMF constant KB is given that 0.5 volt per RPM. Armature current IA is 5 ampere. Armature resistance is 2 ohm. Now, the converter is working from 220 volt single phase AC source with a firing angle of 30 degree. Under this operating condition, what is the speed of the motor? Okay. So, source voltage to the converter. Source to the converter. Okay. What is that? Single phase 220 volt, frequency is not given, leave it, and firing angle is given 30 degree. Okay, firing angle is given as a 30 degree. Therefore, from this data, what I can calculate first, output voltage of the converter V0, which is equal to terminal voltage of the DC motor. What is the formula for that? Single phase half controlled converter. Okay, that is Vm by pi into 1 plus cos alpha. So what is Vm here? 220 into root 2 divided by pi into 1 plus, this voltage is 184.8 volt. So this is the terminal voltage given to the motor. Okay. Now what could be back EMF? Vt minus Ra into Ia. So 184.8 minus armature resistance is given 2 ohm, armature current is given 5 ampere. Therefore, it will give you 174.8 volt minus 10. But what is given here for every, what is the meaning of back EMF constant? For every 1 volt, the back EMF is 0.5 volt. Therefore, how can you express this EB? KB multiplied with the speed. So, N is equal to EB 174.8 divided by 0.5, 349.6. You can say approximately 350 RPM. So, 350 RPM, that is the answer. Now, let us take another problem. A 3-phase 440 volt 50 hertz AC mains fed thyristor bridge. What do you mean by the converter circuit given here? Converter is three-phase full converter. Source to that converter circuit. Source to that converter circuit is 3-phase 440 volt 50 hertz. Okay. Now it is feeding a DC motor whose ratings are, now the DC motor ratings, (440 volt is the terminal voltage, 15 kilowatt, speed is 1500 RPM, separately excited DC motor with a ripple free continuous current in the DC link under all operating conditions. So what do you mean by that? You can say that armature inductance is sufficiently large enough to maintain armature current to be continuous or constant current armature current, neglecting the losses. Therefore, you can neglect the armature resistance and all. Now, the question is, what is the power factor of the circuit? You have to calculate power factor. You need to calculate what is the power factor of the circuit. So first let us do few basic calculations. I can start with this formula, V naught is equal to Vt. Okay. What is V naught here? That is 3 VML by pi cos alpha, because converter is 3-phase full converter. Output voltage of 3-phase full converter in the rectifier chapter we learned, that is 3 VML by pi cos alpha. Now what is mentioned here, it is operating under rated conditions. Okay, that means the terminal voltage of the motor is 440 volt, converter is providing that 440 volt. So what I can say, Vt is equal to 440 volt, because machine is operating at a 440 volt. Now what is the power factor of this circuit? Input power factor of 3-phase full converter is, input power factor of 3-phase full converter is 3 by pi cos alpha. So from this formula, if you extract 3 by pi cos alpha, what you will have? 440 divided by VML. So VML is peak value of AC source voltage. Okay, that is 440 into root 2. 440 into root 2. Okay. So what is answer here? Under all operating conditions, again one more point I forgot here, we need to calculate the power factor of the circuit at half the rated speed. Half the rated speed means what? Terminal voltage is equal to back EMF, isn't it? When terminal voltage is equal to back EMF, that means by neglecting the losses, means armature resistance is 0. Therefore, this is 1. Now, input power factor of the full converter is 3 by pi cos alpha. At rated speed means, at half rated speed. Therefore, what you have to take here, you should take terminal voltage half, because when the speed is reduced by half, terminal voltage will also be half. So you have to multiply this with 1 by 2. So 1 by root 2 is 0.707 into 0.5. It will give you 0.3535. Power factor of any rectifier circuit is always lagging. So for this question, answer is option A. Now let us take one more problem. A 220 volt, 20 ampere, 1000 rpm separately excited DC motor has an armature resistance of 2.5 ohm. First let us note down the data. Solution. What is given here? Separately excited DC motor. Separately excited DC motor. Its ratings are 220 volt, 20 ampere, 1000 rpm, and armature resistance is 2.5 ohm. The motor is controlled by a step down chopper. So here motor armature side, what is the converter is given? Step down chopper. So earlier it was a rectifier circuits, you have used output voltage of the rectifier circuit. Now as a converter is step down chopper, you have to use output voltage of the converter, that is D into VDC. Okay. Input voltage to the chopper circuit is 250 volt. So input to step down chopper. Input to step down chopper is VDC is equal to 250 volt. Observe carefully, whenever these two numbers are given, you should be very careful. That 220 volt is the rated voltage of the DC motor, but this 250 volt is source voltage of the chopper circuit. Now what is the question? Find the duty cycle of the chopper for the motor to operate at a speed of 600 rpm while delivering the rated torque. That is important in this problem. So what I can say here, first, at rated conditions, let us calculate back EMF first. Let us call it EB1. So how to express that? 220 minus 20 into 2.5. So 20 into 2.5 is 50. 220 minus 50 will give you 170 volt. Back EMF under rated conditions is 170 volt. Now I can say that EB1 is equal to 170 volt at a speed of 1000 rpm. At a speed of 1000 rpm. Now what is the question? Find the duty cycle ratio of the chopper for the motor to operate at a speed of 600 rpm. Therefore, what is the equation we can take? EB2 divided by EB1 is equal to N2 by N1. Okay, that means back EMF under second condition is EB2. Therefore, EB2 is equal to 600 divided by 1000 multiplied with 170. So this is a 60% or 0.6 into 170 will give you 102 volt. 102 volt. Okay. So this is the back EMF at speed of, let me write down here, at speed of 600 rpm. Now you need to find out, corresponding to this back EMF, what is the duty cycle ratio. So what could be our equation? V0 is equal to Vt. Am I right? But what is V0? V0 is output voltage provided by step down chopper. That is D into VDC is equal to, what is Vt in the second case? EB2 plus IARA drop. Therefore, D into input voltage to the chopper is 250 volt is equal to back EMF we got 102 plus armature resistance is 2.5 into, now here the question is, what should be armature current? Here it is mentioned clearly that when the machine is delivering rated torque, as the torque is rated value, armature current will also rated value. Okay. Therefore, I can simply take rated armature current, that is 20 ampere. So D is equal to now 102 plus 50, 152 divided by 250. So this value is 0.608. This is the answer. That is option B. Now let us take another problem. The separately excited DC motor has a rated armature current. It should be current. A rated armature current of 20 ampere and rated armature voltage of 150 volt. An ideal chopper with input voltage of 200 volt switching at 5 kilohertz is used to control the armature voltage. If armature inductance is 0.1 millihenry, armature resistance is 1 ohm, neglecting armature reaction, find the duty cycle ratio of the chopper to obtain 50% of the rated torque at the rated speed. Now here speed is rated speed, but torque is a 50% rated torque at the rated field current. So just like previous problem, first what I can calculate here, at rated conditions, first calculate back EMF EB1. So what is that? The voltage is, rated armature voltage is 150 volt minus armature resistance drop 20 into 1 ohm. So this will give you 130 volt. Okay. So this is at rated speed. Now at the required conditions, okay, at required conditions, what is the back EMF? As the speed is reduced by half, at rated speed and rated field current. So there is no change in the field current as well as the speed. Therefore, at required conditions, what will be back EMF? Same 130 volt only. But what will be armature current? As the torque is reduced by half, field current remains same. Therefore, 20 by 2, 10 ampere. I hope you are following. It's a simple machines concept. So, as the torque is reduced by half and field current is the same, because T is proportional to flux and armature current. Flux is same, torque is reduced by half. Obviously, armature current will also reduce by half. Therefore, under these conditions, again you can start with the basic equation. V0 is equal to Vt. As the circuit, as the motor is driven by a chopper circuit, you can simply take D into VDC in the left side. Vt is nothing but, now second conditions, EB2 plus RA into IA2. Therefore, what is EB2? 130 plus RA is 1 ohm. Here, armature inductance is given just to confuse you. There is no need of armature inductance here because this is a completely steady state analysis. So, in the steady state analysis, voltage drop across armature inductance will be 0. RA multiplied with IA2 is a 10 ampere. Okay, left side D multiplied with what is the input voltage to the chopper circuit? That is 200 volt. 200. So this will give you D is equal to 140 divided by 200 is equal to 0.7. Okay, this is equal to 0.7. So answer for this question is option D.